So, welcome to the Astracast for the Starlink mission today, which is going to be launching aboard a Falcon 9 rocket. Of course, Falcon 9 is a rocket that's built by SpaceX. And so, let's watch along and find out a little bit about the Starlink missions and also about the Falcon 9 vehicle. Of course, if just a little bit about who we are, I'm Josiah Coy. I'm the chief engineer at Astra Bremen, which is a university student group which is trying to build a rocket which goes to the Kármán line. The Kármán line is, of course, the boundary between Earth's atmosphere and space. So yeah, this is a project that we're trying to undertake, and we're just trying to get to space, not stay there. Of course, today the Starlink satellites are actually going to go into orbit, which is different from the orbital profile that we were trying to get into. We're just trying to go into space and then we come right back down. But of course, these guys are professionals at SpaceX, and so maybe we can learn a little bit about how their vehicle works and maybe a little bit about the technology that they're using, and definitely a little bit more about the Starlink satellites. Of course, you may have heard lots about Starlink over the past couple of years as SpaceX has been developing this constellation. But yeah, there's definitely some interesting things to talk about with respect to that because there have been some interesting news pieces that maybe we can discuss a little bit while we wait here for the last 10 minutes of the launch. And of course, let's always be ready to potentially be disappointed today because so there can be delays at any point, so keep that in mind. This is a rocket launch, and none of us have our crystal balls. There are lots of things that can go wrong, of course, in the lead up to a rocket launch. So just to start off, I guess we should probably discuss a little bit about what Starlink is. So Starlink is this giant communication constellation that SpaceX is developing that's going to supply communications, specifically Wi-Fi, all around the world. And specifically to places where there isn't much fiber optic cable already going to it. And basically Starlink can use its space-based setup in order to supply internet basically anywhere you live in the world. Right now, Starlink's already operational and it's already providing these services. So yeah, you can actually check out a Starlink coverage map, which I have have got a little bit aware of this, that this might be a problem, and they don't want to take these risks anymore with the geomagnetic storms, and they're actually planning to launch the satellite into a slightly higher orbit this time. So they should be not suffering the same problem again, hopefully. Of course, when they in order to launch into a higher orbit, they need to have a little bit more fuel that they have to use, so they can't quite take as many satellites. At the start of these launches, when they were doing it back in 2019, 2020, they were taking 60 satellites, 58 satellites, but today they're just going to take 50. So this is kind of typical of their newer launches, where they're taking less satellites but trying to make sure that they all get to their destination. Let's talk a little bit about the Falcon 9 vehicle itself. But yeah, let's get back to the launch here, and let's see where they are in the countdown.
Cup of water sitting on sitting on your table, you start to see those beads of water form around the cup. It's a very similar interaction. So in about 30 seconds here, we are expecting to hear the call out for second stage LOX load complete. This will wrap up propellant loading for the entire vehicle.
So it looks like they're just finishing up with loading there.
We have 50 Starlink satellites inside the fairing at the very top of the rocket. This is SpaceX's 8th mission of the year.
So yeah, we're coming up on the launch here pretty soon with 2 minutes left. It looks like everything is green. I don't think they have any range problems, and I think we're good for weather. It's looking quite nice.
T0, just under 2 minutes now. Again, the range, vehicle, and payloads are all looking healthy for an on-time liftoff, just about a minute and a half.
Stage 2 LOX load is complete.
From now. And there was the call out for stage 2 liquid oxygen loading complete. Again, that is the last of propellant loading. We're going to start to see more clouds start to form around Falcon 9. Again, we are venting that liquid oxygen and trying to top off the stages as much as possible to keep the propellant inside the rocket chilled.
Those clouds that are forming are just because the liquid oxygen is so cold.
In the countdown.
And basically, when it boils off in the tank, it comes out at over minus 100 degrees Celsius, and it essentially condenses all the air around it.
So we are in startup. Both stages are now beginning to pressurize for launch, and in a few seconds here, we're going to be hearing the launch director give their final go for liftoff.
We've never seen that camera view before on the other one, where it's you see it just.
For launch.
And there it is. All systems are go for launch. Let's listen in to terminal count and watch as Falcon 9 takes our 50 Starlink satellites into orbit.
I should point out that today they're launching from Vandenberg Air Force Base, which is over in California, and not from the Cape in Florida. And the reason for this is that they're going into a highly inclined orbit, so
T-minus 15 seconds.
they don't need to be launching from Florida for the normal eastward trajectories that you would
10,
take.
9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of Falcon 9, Starlink 4-11.
All right, here we go. Everything's looking pretty good so far.
M1D chamber pressures are nominal.
So watch out for max Q. That's going to be the next part of this mission here. Basically, that's the point where the vehicle is having the most pressure on the vehicle because of the air drag. And that's going to be coming up in about 30 seconds or so. The vehicle will be at a speed of about 1,400 kilometers per hour when you see that.
T plus 42 seconds into flight, Falcon 9 has successfully lifted off from
Power and telemetry
Vandenberg
nominal.
Space Force Base, carrying our stack of 50 Starlink satellites to orbit. And a moment ago, we began to throttle down the engines on the first stage in preparation for max Q. This is where the vehicle will experience the highest amount of pressures during ascent.
So just past the sound barrier there.
Max Q.
And there was max Q. So we have a couple of events happening in quick succession in about a minute. First up, we'll have main engine cutoff, also known as MECO, followed by stage separation, and then second engine start run, also known as SES1. First up, main engine cutoff. This is where all 9 engines on the first stage will shut down in order to slow the vehicle down in preparation for stage separation. During stage separation, the first and second stages will separate from one another. The first stage will make its way back to our targeted landing zone. In this case, it's the drone ship, Of Course I Still Love You, currently waiting in the Pacific Ocean. And the second stage will continue its journey with the third event, second engine start 1. This is where the single Merlin vacuum engine on the second stage will ignite and propel the second stage along with the Starlink satellites into orbit.
So you can see the plume is getting really wide. That's just because the atmosphere is way less dense up at 50 kilometers where they're flying right now. So the engines are optimized for sea level, and now the air is getting much less dense. And here comes stage separation up real soon here. We'll get a good camera view of it.
MECO. Stage separation confirmed.
There you go.
MVAC startup.
And the fairing should deploy relatively
Did have
soon here.
Successful main
Fairing
engine
separation
cutoff,
confirmed.
stage separation, second engine start of the Merlin vacuum engine, and you just saw on screen that the fairing halves have been deployed from the top of our second stage. We've been flying.
So you can see that the grid fins just extended, and these are those like waffle-looking things on the side of the main booster, and those are going to be what is going to allow the Falcon booster to navigate when it's in the lower parts of the atmosphere. But while it's high up in the air right now, it's going to use those thrusters that you see. Sometimes you'll see a white puff of smoke on the left-hand screen, and those are little cold gas thrusters that the booster is using to orient itself when there's no atmosphere that it can use to help fly through.
To carry our stack of Starlink satellites to low Earth orbit.
So yeah, it'll be a
And
couple
these
of
are
minutes here.
Live views. In order for the first stage to make its way back to our drone ship, it needs to execute 2 burns. The first is an entry burn where 3 of the engines on the first stage will reignite, and this will help to slow down the stage as it re-enters the upper parts of the atmosphere. The second burn for the first stage is the landing burn. This is a single engine burn that will bring the vehicle's speed down rapidly in order to land on our drone ship. So a few minutes away from those entry and landing burns. For now, we're enjoying some great views of both stages.
Yeah, so Rocky Tyson, the thrusters that are
The
on
engine that you
the
see on screen
main
on the
booster
second
there
stage.
are, yes, they are nitrogen thrusters. So uh, they're not using any chemical reactions to create thrust. It's just the cold gas that's being stored inside of basically they store them in these carbon composites tanks, and they just open a valve, and that's how you and let the gas out.
Thrust. 190,000 pounds of thrust each.
And that strategy usually creates really good reliability, which is kind of what they want, and it's super simple. Yeah, on the right-hand side, though, you can see the Merlin engine, and
So on the left-hand side of the screen, we see some puffs of gas. That is nitrogen gas from our attitude control systems. And on the adjacent side of that, those puffs of gas, you can see 2 of our 4 hypersonic grid fins. These help to steer and guide the first stage back.
yeah, I suppose nitrogen is good for the plants. Yeah. I mean, I don't think there's going to be many plants up at 100 kilometers of altitude, though. So I'm not sure this nitrogen will get to them.
And help it land as well. We're just under 45 seconds away from the first of those 2 burns, the entry burn on the first stage. Again, it is a 3-engine burn to slow the stage down before hitting the thicker parts of the Earth's atmosphere.
So we might lose connection with the booster during the reentry burn and just after the reentry burn, because the reentry heating of the atmosphere causes basically a radio blackout, and it's hard for the signals to get through. So don't be too worried if we lose connection.
Continuing to go smoothly for our second stage.
Should be coming up pretty soon here. There we go.
Stage 1 entry burn startup.
And you can see on screen, 3 of our 9 engines on the first stage have relit and are currently slowing down that booster.
And this burn
is
is
expected
actually
to last-
what causes the rocket to get all sooty when it comes back. It's because the exhaust plume is basically being thrown back onto the rocket during this phase.
Burn to go on the first stage in about a minute.
Stage 1 FTS is safe.
After the landing burn ends and
Yeah.
we attempt our landing
We just
on
lost
our
the signal
first
there.
stage, we're going to be listening for the call out for SECO, also known as second engine cutoff 1, and then a confirmation of good orbit. For today's mission, we are going to be having 2 coast phases. So after we shut off our second stage engine that you see on screen, we'll coast for about 40 minutes, and then we will actually relight the engine for a few seconds, and then coast again before we deploy the satellites about T+1, a little after T+1 hour into the mission.
Stage 1 transonic.
Yeah,
We did lose video footage of the
main products of the exhaust of most rocket engines is actually just water. So it's also contributing to the water cycle, I guess. They're seeding some clouds.
make its way to our drone ship.
Okay, hopefully we get a drone ship
Stage
picture
2
here.
FTS is safe.
Ah, there we go.
And here's
Stage
a
1
view
landing burn.
of our drone ship. We just heard the call out that the stage 1 landing burn has started. So if we are successful, this will be the 4th time that this booster has successfully landed.
Looks like we're not going to get the picture.
Stage 1 landing leg deploy.
Hearing callouts that we did get the landing legs deployed.
Sounds like it worked.
Waiting for audio or visual confirmation of that first stage.
Ah, there we
and
go.
There
Stage
it
1
is.
landing confirmed.
Right in the middle of our drone ship.
SECO 1.
That is a successful first stage landing, the 4th for this particular first stage booster.
I feel like they're getting more precise on each
So we
landing.
did hear call out for successful second engine cutoff of the Merlin vacuum engine.
insertion.
And that was the call out we were waiting for as well. Nominal orbital insertion. So now the second stage with our satellites are in a coast phase. Next up is second engine start 2, also known as SES2, and second engine cutoff 2, also known as SECO2, which is scheduled to start around the T plus 53-minute mark. From there, we're going to have payload deploy occur just after the T plus 1 hour mark. Until then, we're going to take a short break, and we'll see you all back here in about 45 minutes. Until then, sit back and enjoy the space jams, and we'll see you soon.
All right, so yeah, that was quite exciting. One thing to clarify a little bit is one question that we often get is, why does the signal get lost when the rocket is about to land? It's a little bit, I don't know if you have any conspiracy theorist friends that think that the booster is not actually landing and they're just showing pictures at the very end. But what's actually happening there is the boat that is catching the rocket is on the water, so it's bouncing around up and down and up and down, and this causes there to be it's difficult to maintain a signal when you have a dish that's on the boat that's connecting to some satellite, because the angle that it's pointing is changing with the waves. And it gets especially bad when the rocket is coming in, because it vibrates everything so violently. So it's really hard for them to maintain a signal in that phase. So usually the drone ship camera will always cut off right at the very end. And sometimes you get the rocket camera might stay on, but usually it cuts out after the entry into the atmosphere, and then that's basically all you get. It's far more impressive, in my opinion, to watch the ones that land on land, because then, of course, you can't really shake the land so much that you will vibrate the cameras and the signal device. So usually you get a clear shot all the way right to the ground. So those are always, in my opinion, the best to watch. But yeah, it looks like they have a successful mission today, with successful launch of the 50 Starlink satellites into orbit, and then we have a little bit left in the mission, coming up in about 40 minutes, I guess. And then, yeah, everything should be working pretty well there. Usually they don't have a problem at this point. With the return of the booster, that's also good to see. Like they were saying, this is the 4th reuse of this booster, so this one still is a young one, I would say, because the most reused booster is one that's been reused 11 times. So they're getting quite good at really cycling through these and starting to kind of use them at a point where it's almost like they're an aircraft. So this is actually quite an interesting point in spaceflight history, where we're on the verge of really having rapidly reusable rockets. So this is really a cool thing about what SpaceX is developing and what they're doing with the Falcon 9 rocket. Yeah, we also hope that the payload, the satellites, will continue their journey onto orbit happily without getting caught in any storms or anything. But I think this shouldn't be too much of a problem, because, like I said, they are going into a slightly higher orbit this time, so it shouldn't they shouldn't get disturbed by the tyranny of the sun. Yeah. If there are any questions left, feel free to ask. I think I'll stay online here for another 5 or 10 minutes if you guys are curious about asking. I'm a space engineer, so there might be some things that you're wondering that maybe I can clarify a little bit. And also, if you're interested in any questions about Astra and our student group that is looking to build a rocket of our own that will get into space, of course you can ask about that too. Yes, of course. Yeah, like Anton, yes, 40 satellites were lost, and the reason why they were lost is because of the density of the atmosphere that was caused by the geomagnetic storm. So basically, in a geomagnetic storm, the sun heats up the sun's atmosphere, or the solar wind, interacts with the magnetic field of the Earth, and that heats up the upper atmospheres of the upper atmospheric layers of the Earth. And when things get hotter, it causes them to expand. So basically, the lower parts of the atmosphere end up going higher up. and the lower parts of the atmosphere are more dense. So you end up having way more density in the orbit than what you were expecting. And that's basically what happened with the Starlink satellites. The density increased by 10 times what they were expecting. And so the little thrusters that are on the Starlink satellites just weren't strong enough to fight against the atmospheric density that they were suddenly having to fight against. But yeah, I think over the course of the entire Starlink program, let's take a look. Let me just. So yeah, I think that the strategy that they're using with focusing more on cheaper satellites is actually probably going to be more positive in the end, because essentially they can assure that, okay, if they lose some satellites, it's not such a big deal because they can launch another batch of 60 of them or 50 of them in the snap of a finger, basically, because they have a Falcon 9 standing by. They have a whole fleet of them, and they can launch them for such a cheap price at this point that it doesn't really even matter if they lose a couple hundred of satellites, to be completely honest. So that is one unique advantage that they have. This is, of course, in contrast to a company like OneWeb, who has to keep going to market to find to launch their satellites. So they have to buy a whole other Soyuz in order to launch these. And so yeah, this is one advantage that Starlink has, is that they have a rocket company on standby. Is Musk in trouble with the SEC? I don't know about this. He's always in trouble with the SEC, to be honest, because the way he posts on Twitter and stuff is, I would say, a little bit un-CEO like. Yeah, basically a lot of his companies are sometimes dictated by what he puts on Twitter, so it's a little bit questionable how the way he uses it. But yeah, I don't know anything about finance really, and I don't know what the rules are, so I don't know if he's in trouble with the SEC. It happens. I'm sure that they'll just fine him some small amount of money and he'll not really care in the end. That's usually what happens. Yeah. Yeah. Musk is like the Trump of engineers, right? Just does whatever he wants, makes fun of other companies for doing things when he doesn't like the way they do it. Yeah. That's something that's unique and special about him, though, because you really get kind of a window into what he's thinking and, his general strategies behind how he runs his businesses. And that's something you don't get from other CEOs. Like, like you probably don't even know the names of the CEOs of Boeing or Lockheed Martin or United Launch Alliance. Like, they're not really in the public space. So it's nice that we get a window into what's happening with SpaceX and Tesla and the companies that Elon Musk is involved in. Like, as an engineer anyway, I think it's fascinating because you just wouldn't get this information from other companies. Yeah, so just to follow up with Rocky, yes, we are into very high power rocketry. So we're a group out of Bremen University in Germany, and we're planning to build a rocket which is going to go to the Kármán line. And to do that, we're designing a hybrid rocket, and basically we need to have this rocket have a thrust of about 24 kilonewtons in order for us to achieve what we want. I think that would put us at about number 3 on the list of the most powerful student rockets developed. So, and we're maybe going to need to step that thrust up to maybe just above 25 kilonewtons, which would put us at number 2. So, yeah, it's definitely going to be interesting once we start testing this vehicle, and we will certainly post that stuff onto the YouTube channel. So yeah, you'll definitely get some live action there. Hopefully it's not too exciting though. We might get some explosions as well, but we'll see. We're hoping for the best still. We're a little bit new to the high power rocketry world, so yeah, it's definitely going to be a high learning curve. But the plan is to start testing this summer with that hybrid rocket. Yeah. Yeah, the other group to look at that is going to be definitely really interesting this year is Space Concordia. They're a Canadian group, and they are going to be launching their Star Sailor rocket sometime this summer as well. And they have a really high power rocket. It's 37 kilonewtons, and that is the highest power rocket that's ever been developed by a student group. And they've built this basically just monster of a rocket. And we've talked a little bit about it on the channel. I think you might be able to find some of the videos on it. But it's an absolutely epic vehicle. And when it takes off, you should definitely be watching. I think they're going to be live streaming it, so definitely stay tuned for that. I'm definitely looking forward to it. And they are also trying to get to the Kármán line. And yeah, I think they have a good shot at potentially getting there. Yeah, and it's also a liquid rocket, which is just even more crazy because like just to develop a liquid rocket is such a challenge for student groups because they're usually a lot more complicated. But yeah, they've managed to figure out some of the biggest problems related to that, and they've managed to test it even through the whole COVID period. It's just crazy. Yeah, so thoughts on a two-stage design. Yeah, two-stage designs are usually complicated to manage and test. Basically, in most two-stage designs that you have with a suborbital rocket, you have to be staging at a very unstable aerodynamic state, if that makes any sense. So to make it make sense, usually you're going to be staging somewhere in the transonic regime. And that can be complicated and can complicate your aerodynamics. And you also need to make sure that your whole separation system is powerful enough to fight the friction that you're going to have at those speeds and altitudes. And everything has to flow really, really well. And I've seen there's definitely been there've been a couple examples of students and amateurs pulling off two-stage designs that are quite high performance. But it definitely requires a little bit of expertise and definitely not, first crack at it, I would say. You have to have a little bit of experience with with flight in those regimes. So we've kind of decided that wasn't the best solution for us, and I think a lot of groups that are not having so much experience probably would settle on that as well. But yeah, there is something to be said in some cases for a two-stage design. For most hybrid and liquid applications, the mass increase that you need in order to achieve a technically reliable separation actually sometimes ends up in a higher overall mass vehicle than if you just did it in one stage in the first place. So it's kind of like, well, if you're not really gaining much, or if you're not even getting anything at all in some cases, why not just make a single stage? So that's kind of why we've chosen the single stage at this point. But yeah, one group that did a two-stage was, this would have been way back like 15 years ago, was Embry-Riddle University. They, what was their rocket called? The Icarus. And they had a two-stage design, and it went all the way up to about 80 kilometers. It was all solid rocket. I think that's probably the most successful amateur one I can think of. But yeah. Yeah, we have a staging system on the rocket, but it's not really a rocket staging. It's just to separate the nose cone from the vehicle itself, and that's already a really complicated system. Like we're already racking our brains on how we can test this thing and make it, somewhat reliable. I can only imagine how difficult it would be if we had to actually stage two pieces of a rocket. Like that would be way harder to try and figure out. Yeah. Yeah, it's pretty crazy how fast that stage is. Now it's already flying over South America. It feels like it's been like 5 minutes. My goodness. It's yeah. To give you an idea, there's quite a big difference between getting to space and orbital and going orbital. So the rocket that we're designing that's going to go into that's going to go to space is just going to hit a maximum speed of about Mach 4.5. So that's about 5,000 kilometers per hour. But to go orbital, you have to go about 28,000 kilometers an hour. So it's almost like 6 times more velocity that you need to get. So it makes sense to make a two-stage rocket when you're just going to orbit, because you literally are running into the edges of what structures and propulsion technologies can achieve in terms of delta V. But for a suborbital flight, you're still well within the range of what you can achieve with just a single stage. Yeah, that's actually another good point with respect to the burn duration. One of the main challenges that we're having right now is actually with figuring out where we can launch, because basically when you have a vehicle that is going on a suborbital hop like this and you don't have any control of the rocket, sorry, let me rephrase. When you don't have active control of the rocket, so we basically just have a rocket with fins on the bottom and they passively stabilize the vehicle. So in those situations, you're very sensitive to the wind, because if the wind is blowing, the rocket will, because it's passively stable, it'll just turn into the wind. So if you think about this, if you're at the launch site and you want the rocket to go over into the ocean, and there's a wind that's blowing towards the ocean, your rocket will come off of the launch tower and it'll point towards the wind and end up going back onto land. So usually, in order to avoid this, you want to get up to a really high speed before you exit the launch tower. So you need lots of thrust at the start. And usually in order to achieve that, you need to have a really short burn, because if you have a longer burn, you have less thrust when you're getting off the launch tower, and then your rocket is really sensitive to the wind and can kind of end up going anywhere. And that makes the launch site really nervous, and it can be really hard to get approval so that you can launch your rocket at the launch site. So this is one thing we're dealing with right now, is how do we prove to the launch site that our rocket will not become a uncontrolled missile and blow up someone's house. Yeah, so that's another thing that is a complication, because if you have a two-stage system, usually you have a longer duration burn. And what happens if the separation goes wrong and something happens and the rocket ends up pointing the wrong way and the second stage lights and poof, you're outside of the test range? Yeah, that can be difficult to manage. We're a European student group, so we have to think also about the European community where we're launching, and usually the places that we can launch are a little more densely populated. It's not like America where you can just literally drive out to the desert and it's like, all right, let's go launch a rocket. Or in the middle of northern Canada or something, where like your rocket can go anywhere, and it's all it's going to do is maybe hit a polar bear or something. But yeah. Yeah. One thing that was a little bit shocking with designing this rocket was actually having to do with aerodynamics. Surprisingly, the aerodynamic drag that we're expecting to take during this flight is consuming about 1/4 of the thrust budget. So what that means is that if there was no atmosphere at all on Earth, our rocket could go it could have 1/4 more total impulse. So it could probably get to an altitude of 200 or 300 kilometers in that situation. So it's pretty crazy how much drag the atmosphere actually imparts on your rocket that's just quickly shooting through the atmosphere for 15 seconds. Yeah. Okay. So yeah, the paperwork. We know all about the paperwork. This is definitely always a challenge. But yeah, definitely. Good luck with the end motor altitude shot. Wishing you all the best for getting that done. What's the altitude that you're shooting for? I'd be curious. Yeah, but the paperwork's always a problem. But it just has to be done, gotta have that paper trail. We have just started our application with the civil aviation authorities at the various launch sites that we're trying to get approval for. And yeah, it's definitely a process. It's going to take us probably 9 to 12 months just to go through everything and get the final go ahead. And then of course there's also the reviews. We have 2 major reviews that we're going to conduct. One of them we're doing right now, which is the preliminary design review, where we're basically presenting our entire design methodology to the German Aerospace Agency, and they're giving us comments and stuff about our design. And then we have another one called the critical design review, which is a more in-depth version of that, where we consider also some of the testing data that we've collected. And yeah, so we're no stranger to the paperwork, that's for sure. Wow, 60,000 feet. That's quite a go for it. That would be a very high performing vehicle indeed. Yeah. Well, I wish you all the best for getting to that altitude. Definitely put a camera on it. You'll get some really cool views. One thing that we're still debating right now is whether we want to de-spin the rocket when we reach the target altitude. Because obviously, if you want to get good pictures, you need to, your vehicle can't be spinning at like, 4 or 5 hertz. And it's just the picture just looks like a blur. But it also takes mass to de-spin it, because you have to use like a yo-yo de-spin system or something. But yeah, we have to make sure we have enough mass budget to accommodate that. But yeah, it's always cool to see how many amateurs there are working on various rocket projects. It's definitely a what I would call an impassioned community. Good to hear you have the GoPro. Love to see the footage. Yeah. It's not official unless you have the camera footage, right? One thing that I was thinking of setting up is I want to set up like a website where you can go and you can see all of the highest like altitudes and achievements for various different categories in the amateur community. I don't know if you saw the video that we did about the highest flying vehicles of 2021, but I kind of want to create a database where we can see like what the past has been for rocket launches in the amateur community, and what the records are, and what the vehicle specifications of different people and groups are, because I think there's a lot of there's a lot of awareness about each other in the amateur community, but we don't really always know what everyone's doing in various different places. And sometimes people think they're breaking a record, but they're actually not breaking a record, or they have different definitions of what the record is. So I would like to create kind of like a central place where all of that information is stored. And maybe we could have a way where people like submit their altitude data to the website, and then you can have like an official record after you complete your mission. I think that would be good for the amateur community, because I definitely being on both sides of the Atlantic Ocean, because I actually am Canadian by citizenship. There's not a lot of communication, I feel like, between North American and European rocket groups. So it would be nice to have some, how shall I say, universality between the two worlds. But yeah. So we have about 10 minutes or so left until we're going to see the last bit of the mission here. Just to describe a little bit about what's going to happen. Sorry, we're segueing back to the SpaceX mission here. Basically, the rocket is going to light its engine for about a second or two more when it reaches the apoapsis of the orbit. And the reason why it does that is because right now it's on elliptical orbit. It's going from about 200 kilometers all the way up to 300 kilometers or so, and it needs to circularize that. And then after that, it'll release the satellites. And the way it does it is by spinning. So the second stage of the rocket will actually put itself into a tumble, and then it'll just release the 50 satellites just by like unlatching them, and they'll kind of just spin away. And because they're all at different like heights through the stage of the on the deployment mechanism, each of them has a little bit different rotational inertia, And basically the ones on the outside will fly out faster, and the ones on the inside will fly out a little bit slower. And so they kind of naturally just float away without hitting each other. That's the idea anyway. Oh, I didn't know that the website actually exists. Interesting. I would be very interested in knowing the link to that website, because I've been searching and I can never find it. I can never find access to that kind of data. But if they have it for Canada, then surely they must have it for some of the other countries as well. What is the Canadian altitude record anyway? I don't even know what it is. Is it over 10 kilometers? Surely it must be. I think the University of Toronto had a rocket that went over 10 kilometers at one point. And if you're Canadian, Rocky, why are you measuring in feet? What's up with that? 44,000 feet. Okay. So what is that? That's like 10. That's like 12 or 13 kilometers. Yeah. O power motor. Yeah. Yeah. If you want to get up to, if you want to start getting up into the 20, 30, 40, 50 kilometer ranges, you probably might have to switch to maybe some higher power solid solutions or hybrid. The car website, okay. I'll have to check that out. Definitely for the Canadian records anyway. Still would be nice to have one that's for the whole world as well, though. Yeah, but I look forward to your record-breaking attempt for the 60,000 feet. That should definitely be exciting. Yeah, nothing wrong with using feet. It's perfectly okay. It's all just a measurement unit, right? Yeah, one thing that I had, because obviously I grew up in Canada and did my high school in Canada, so I always did things in meters because I'm, I guess, young enough when they were only teaching in meters at that point. But then when I went to school in America for my bachelor, it was all in feet again. So I'm always switching back and forth. And now I'm back in Europe and we are always in meters. So yeah, I'm always switching back and forth between feet and meters. Yeah. I think that at least amateur rocketry in Canada seems to be picking up a little bit in the last couple of years, because I'm hearing about a lot of different student groups for sure that are starting to develop higher power rocketry, and there's a couple of groups that are all starting to think about eyeing the Kármán line as their target. So it would definitely be nice to see some of those succeed, and of course Space Concordia being the darling of the bunch. Yeah. One thing that's a little bit unfortunate is that all of the world altitude records are all held by Americans. So like the world amateur rocketry record for all amateurs is held by an American group. What are they called? The Civil Aviation something. I'm getting the name wrong. But they had the Go Fast rocket, and that went up to about 117 kilometers. And the student record is also held by an American group. at the USC Rocket Propulsion Lab. They went to about 103 kilometers. Yeah, Canada's always in this weird half world where they're like half metric and half imperial. Like we measure our roads in kilometers, which is metric, but then we measure our weight in pounds. Like Canadians won't tell you how much they weigh in kilos usually. And we measure how tall we are in feet, and we measure how much we eat and stuff, and how we cook. We usually measure in imperial units. But then yeah, we like other things are metric, and it's like kind of weird how we just seamlessly use both units for some reason in our regular day lives. The American influence is quite strong. Yeah. I had to get used to that also when I was in Germany, is just, figuring out how tall I was and how much I weighed in kilos and meters. So yeah, coming back to the Starlink launch, we're coming up on, I think, about 5 minutes left until 5 or 6 minutes left until we do the second stage activities. And it looks like, what are we flying over now? I can't even tell. Is this Africa? Yeah, we must be underneath Africa right now. So I guess this is going to start somewhere over the Indian Ocean. What would be interesting to see is, and I think will be interesting to see, is in the future, hopefully, some more startups and private launch company startups operating out of Canada. There are a couple that have kind of started in the last couple of years that are trying to move and do small satellite applications into orbit. And one of them is Space Ride. I don't know if you've heard about them, but they are developing a hybrid rocket as well. And I think their hybrid rocket is the most powerful hybrid rocket ever developed in the world. So it's quite a interesting beast. They basically bought some land somewhere in the middle of Ontario, in the middle of nowhere, and they've been testing this rocket out there. But what's unique about their design is they're going to have a balloon that's going to carry the rocket all the way up to like 20 or 30 kilometers. And then they're going to drop it from that balloon, and then it's going to fly to orbit from there. So it's kind of like a air launch system, but instead of launching from a Boeing 747 or something, it's going to launch from this balloon, which I think is an absolutely insane idea. Like, building a balloon that can carry a rocket seems like a bit of a crazy challenge to design. But yeah, if you check out their website, you can see basically their whole test campaign and their design for this thing, and it looks like this like drone blimp that, yeah, it's like this whole mount that's designed to carry this rocket all the way up to those high altitudes. Yeah, and the reason why they do that is because higher up in the atmosphere, there's less density, and you can have much higher expansion ratios on your rocket engine, which causes it to also be way more efficient. And you can get that higher efficiency with a much lower combustion pressure. When you're lower down in the atmosphere, you need really high combustion pressures in the combustion chamber in order to get high expansion ratios. That's kind of what SpaceX does. Like, they have really high in the Merlin engine, and now in the Raptor, like, they're getting combustion pressures of like 300 bar, which is crazy. But if you launch at a higher altitude, like at 20 or 30 kilometers, you can get those same expansion ratios with like a tenth of the combustion pressure. And usually for like a hybrid rocket, that's kind of what you can't really get up to those high pressures with a hybrid rocket usually, unless you do some like special things. So it kind of makes sense for their design to try and do it this way. And then they can get a lot more simplicity. So yeah, I want to see more of that kind of stuff happening in Canada, from these student groups that are, graduating these expert rocket engineers. Yeah, let's go take some risks and see if we can get a space community happening up in Canada. There are some good locations that would be interesting for launch sites for sure. Yeah, there's the old launch site out in Churchill, which is this place up in northern Manitoba by the Hudson Bay that used to be for the suborbital launches way back in the 1980s and 90s. So yeah, it would be interesting to see that starting to get reused more often for some more commercial stuff. But I think there's a lot of other cool places that could work for launch sites. Like definitely somewhere in Nova Scotia, like on the peninsula there, you have like a lot of good places where you could definitely support some orbital launches, where you'd be launching over the Atlantic, either to the east or to the south. There could also be some other good spots up in Ontario, near the Hudson Bay, probably. So yeah, I think there's a lot of opportunity for some space activity in Canada. We just have to take advantage of it. And yeah, Space Ride is just the company that I know about because they have this crazy balloon launch method, and I'm genuinely curious if they can pull it off, and if it will actually be cheaper as they claim. Yeah. All right, it looks like we are getting closer here to the second burn here. Let's not miss it. Yeah. So it's going to be probably about a minute or so left, maybe. He's at T plus 53 minutes, I think. So just to if anyone joined in the last couple minutes, what's going to happen here is the Falcon 9 second stage is going to relight, and it's just going to relight for a couple of seconds. I think just maybe even just 1 second, and it's just going to raise the orbit a little bit, because right now it's in an orbit that's going from 200 kilometers at the periapsis, and it's coming up to 316 or so kilometers at the apoapsis. So it's going to basically circularize that, so the whole orbit is at about 316 kilometers, and that's going to give the safety for the Starlink satellites that they need in order to get them on their way on their journey up to 547 kilometers, which they do on their own with their little thrusters that they have on board. And they need to be that high so that they can fight against the atmospheric drag that is
Welcome back
up there.
to the Starlink webcast. If you are just joining us, a quick recap of today's mission. We had successful liftoff from Vandenberg Space Force Base at 9:12 a.m. Pacific time. Then we had successful stage separation, recovered our first stage after its fourth flight on our drone ship, Of Course I Still Love You, and had a successful second stage MVAC engine burn. Coming up in a few seconds, we'll have the second stage MVAC engine burn, which will be kicked off by SES-2, or second engine start 2, quickly followed by SECO-2, or second engine cutoff 2. This burn is expected to last just about 2 seconds, and so we'll wait on that. Right now, the second stage is just to the east of Madagascar, heading towards Sri Lanka, and there's a view of the MVAC engine that we are expecting to start back up.
MVAC startup and shutdown.
Ah,
And
that was
there
it.
was successful startup and shutdown. Gonna wait for confirmation of a good orbit on the second stage. And so after this, we are gonna coast for a little bit longer before we actually start to deploy our 50 Starlink satellites. But while we wait for that confirmation, I do want to take this time to correct something I said earlier. The white clouds that we saw around the vehicle prior to liftoff is the chilled gas above the LOX tank liquid surface that we vent to maintain pressure in the tanks. So basically, we vent gaseous oxygen, not liquid oxygen.
Yeah, so
Again, we are waiting on
Nominal orbit insertion.
that call out right there, nominal orbital insertion, which confirms that we are in the position we need to be in for the second stage. With that, we're going to take another short break and join you back here just after the T+1 hour mark to catch payload deploy. We will see you soon.
what's crazy is that, so basically it took the Falcon 9 rocket 2 seconds to get it from that orbit from 200 kilometers up to 300 kilometers all the way up to a circular orbit. So 2 seconds. So if the Falcon 9 wanted to get these satellites all the way up to 547 kilometers, it would probably take 5 seconds, 10 seconds. That's it. But it's going to take these satellites that are the Starlink satellites weeks and months to get up to that altitude. So it just shows you how much of a difference there is between the chemical propulsion, which is what the Falcon 9 second stage is using, and the ion electric propulsion that those little Starlink satellites are using. And it's just quite a vast power difference. But the reason why those Starlink satellites use the ion propulsion is because of the efficiency. So usually efficiency is measured in what's called specific impulse. And for a chemical rocket, it'll have a specific impulse somewhere in the range of 300 seconds. But for an ion thruster, that specific impulse can be in the range of thousands of seconds. So you can essentially keep, even though it takes longer to get to where you want to go, and it takes a lot more time, if you plan it properly, you can set it up in a way that you can stay on orbit much, much, much longer. Because those Starlink satellites will keep using those little thrusters in order to maintain their orbit at 547 kilometers. And basically they're able to survive a lot longer than they would if they had chemical rockets or cold gas thrusters on there. So yeah. What is the thrust of those ion thrusters? I actually don't know what the thrust value is, but I'm sure it's on the order of millinewtons. Let's see, maybe I can look it up. I don't know how much they are, to be honest. I don't know if that's even going to be publicly available information. We could probably figure it out, though. We could probably figure it out. Because basically these thrusters are going to be thrusting for continuously. So they basically stay on the whole time. And they're always going to be burning prograde to the orbit. So it'll basically cause the orbit to just slowly spiral outwards. Right, on each orbit. It'll just get a little bit higher, a little bit higher, a little bit higher, a little bit higher. And we know the mass of the satellites roughly because there's the payload mass of the 50 satellites is about 10,000 kilograms, just over 10,000 kilograms, which means that each satellite is weighing on the order of about 200 kilograms. So then you could do some math to figure out, okay, well, how much delta V that they need to get all the way up to 547 kilometers. And how much time does it take to get up there? And then you could probably figure out from that how powerful the thrusters are. But I do not have the time right now to figure that out. That would take me probably 30 minutes of calculation to figure that out. But yeah, maybe on the next stream I'll have an answer to that question. I am fairly sure though that the thrust we're talking about is millinewtons. So You wouldn't if that was thrusting near you, you wouldn't even notice it. That's how small it is. All right. So just to rephrase it or reiterate how exactly the rocket is planning to release the payload, it's going to go into a tumble. So it's going to basically start spinning itself. I don't know, has it started spinning itself or not? Can we tell? It doesn't look like it's spinning yet. But it'll put itself into a tumble, and then it'll just release the satellites. And because of the difference in the angular momentum that each of the satellites has, because it's placed in a separate level in the stack that is on top of the Falcon 9 stage, the ones that are on the top will have slightly more energy, and so they'll start flying away faster, and the ones that are closer will have less energy, and so they'll stay a little bit closer to the vehicle, and basically they'll kind of be strung out like a chain of beads as they fly away from the Falcon 9 vehicle. So a really simple mechanism and really simple theory behind how they can separate all these little satellites and prevent them from hitting each other. And it's always really cool when you can find really simple solutions for complex problems like this. And that's something that I think SpaceX is absolutely phenomenal at
And
doing.
welcome back one final time to our Starlink mission. If you are just joining us, we did have successful liftoff at 9.
And you saw those puffs of smoke? That was the SpaceX rocket putting itself into that tumble.
Stage for the 4th time, and we're just now coming out of our second and final coast phase. On screen right now is a view of the second stage of Merlin vacuum engine. Prior to that, we did see the stack of 50 Starlink satellites positioned on the top of the second stage, and we are expecting those to deploy in the next couple of seconds.
You know, strangely enough, this is kind of my favorite part.
And there were those
Is watching
Starlink satellites that
watching
I
these
was
satellites
mentioning.
just float
Again, there
away.
are 50 of them on top of the second stage for this mission.
Yeah, it's actually kind of just like the Astro rocket, but like you said, intentionally. It's always better when it's something you mean to do. You don't want to be tumbling like that when the rocket is ignited. That's a bad situation.
Earlier in the webcast, we mentioned that these operate at about 550 kilometers in altitude. It actually takes a couple of weeks for the Starlink satellites to use their onboard thrusters to get to their operational altitude. So once we see them deployed from the second stage, they'll kind of distance themselves from the second stage, and then again use those thrusters over the next couple of days and weeks to get to where they need to get to.
Should be coming up anytime now here.
So for those that are interested,
There we go.
Deploy confirmed.
and just as I was saying,
And
that's the
there they
Starlink
go.
payloads on screen. You can see them separating themselves from the second stage, and off they go. So with that successful deployment of our 50 Starlink satellites, that's going to bring our webcast to a close today. I want to thank the Range and Federal Aviation Administration for supporting today's mission. And of course, thank you to all of our viewers and all of our Starlink customers using our service at this time. If you are interested in signing up for Starlink, head on over to starlink.com. But thank you again for joining us, and hope you all have a great weekend.
All right. So yeah, I think that's gonna be it for today. Thanks for hanging out, and chatting about rockets for just over an hour there. It's great to see that the mission was successful, and yeah, looking forward to obviously more successful missions with the Falcon 9 and SpaceX. And yeah, also looking forward to the future of the Canadian amateur rocketry. And also hopefully German amateur rocketry as well, because we'll be technically classified under that category. Yeah, thanks for joining, and look forward to seeing you in next time. And remember to expand your horizons.